All right, I want to talk about one more way of calculating r squared, the coefficient of determination, in kind of a roundabout, but might be a little bit easier of a way, calculating something called the correlation coefficient. It's a little bit more difficult to describe what's actually going on, so that's why I showed you the coefficient of determination r squared, but the correlation coefficient r happens to be a little bit nicer to calculate. So before that, I do need to introduce a couple of notational things for you. So we have these vectors x hat and y hat, and they play a role for us throughout this calculation. And so all x hat is, it's your x vector, and you're just subtracting the mean from each entry in your x vector. So it'll look something like this. The first entry minus the mean, the second entry minus the mean, all the way down, let's say there were n entries, to the nth entry minus the mean. And y hat is similar. You just take all the entries of y and subtract the mean. You're kind of calculating the distance between each point and the mean here. Okay, now that we kind of know our pieces, x hat and y hat, we need a couple of operations. And the first operation is something called a dot product, but it's just a fancy way, in some sense, of doing what's called a sum product. Multiplying the corresponding entries of your two vectors together here, x and y, and then adding those products together. You can think of it as just a fancy way of writing the first vector transpose times the second vector here. So let's kind of write out what this is, and then I'll kind of write out what the calculation would look like. So this is, well, it's x hat transpose, so I'm going to write it horizontally instead of vertically, so it's x1 minus x bar minus the mean, and your second entry would be x2 minus x bar, and you just keep doing that. You get the last one, xn minus x bar, so that's our x hat transpose, and then times our y hat. So this is y1 minus the mean, y2 minus the mean, all the way down to yn minus the mean. And then all this calculation does is it takes the first entry of your x and multiplies it by the first entry of your y, and then adding the second entry of your x times the second entry of your y, etc. So this ends up equaling x1 minus x bar times x times y1 minus y bar. So that's the first entries of our vectors multiplied together, and then we add it to the next one, x2 minus x bar times y2 minus y bar, and we keep going. We do that for all of our terms. And the last one, xn minus x bar times yn minus y bar. So that is our calculation for that dot product there. And then finally, I need to tell you about these things here. And the mathematical word for these is the norm. But for our purposes, we can just think about it as the transpose of a vector times itself, and then take the square root of it. But if you think about what this means just taking each entry of our vector, squaring it, and adding it all together. So the norm of x hat here, well, what is this going to be? This is going to be, I guess I'll write it out first, like this. So it's going to be x1 minus x bar times, and then x2 minus x bar, all the way to xn minus x bar. So there are my n entries. That's x bar transpose times x1 minus x bar, the same thing, x2 minus x bar, all the way down to xn minus x bar. And I want to take the square root of that. And you could think, well, am I taking the square root of a matrix? But think about this. Remember, our vector here is n by 1, n entries. So there are n rows and 1 column. And if we take the transpose, this is 1 by n. So if we multiply these, we end up with a 1 by 1 matrix, which is just a single number. So I can take the square root of a single number, so I will do that. So that's what that looks like. And let me scroll down a little bit just to kind of fill this in. So this kind of simplifies to the square root of x1 minus x bar squared. That's our first multiplication. x1 minus x bar times x1 minus x bar. So that gives us x1 minus x bar squared. And it's the same for all entries. x2 minus x bar squared all the way to xn minus x bar squared. So that's how the norm of x hat works. And the norm of y hat works very similarly, but instead of using your x vector, you use your y vector. That's all that's going on there. So we have our pieces. Let me tell you about the correlation coefficient now. R, I'll give you the formula for that, and then we'll do an example. So here is that formula for a correlation coefficient. So it is the dot product of that x hat, y hat vector combination we were talking about on the last slide, divided by the product of the norms of each of these vectors. So let's calculate something with this formula just to make sure we understand how it works. In fact, let's do the same example that we did in the previous video when we were looking at r squared. So we have the following x and y points. These ones are just from the previous video, so you can look back and check that this is the exact same thing. And we already know what r squared value we got. But when x was 1, we had y was 6. When x was 3, we had y was 4. When x was 5, we had y was 3. And when x was 7, we had y was 2. So they were our data points for our calculation. Now, as a reminder, we ended up with an r squared value of 0.966, which meant our linear regression was a good approximator for our data points, a good estimator. So let's do it the R way, and then we can use the fact, and I'll leave this as a note, that in the case where your linear regression has exactly one independent variable, so in this case x, so we don't have 2 or anything like that. And note that it is possible to do linear regression when you have more than one independent variable, more than one input. But for our purposes right now, we're just dealing with cases with one input, so that's okay. So when you have exactly one independent variable, this correlation coefficient r, if you square it, you get, well, r squared. And that's kind of why these things are named the way they are. Okay, so let's go ahead and calculate r. So let's do that. Let's calculate r for this data set, and we'll show that if we square it, we get exactly what we expect, r squared. So what do we need? We need x hat and y hat as our vectors. Let's scroll and give myself a little more room. Let me write this chart again so I have it. So it was x and y. It was 1, 3, 5, 7, 6, 4, 3, and a 2. Excellent. Okay. So we need to calculate y hat and we need to calculate x hat, but we need the means of the x's and the y's in order to do that. So let's calculate the mean of our x's first. That's 1 plus 3 plus 5 plus 7 over 4, since we have 4 data points. That is 4. You can do a little calculation to check that. And y, the average, 6 plus 4 plus 3 plus 2 over 4. You can check that that is going to be, what is that going to be? 3.75. So we have our averages for x and y. So now we can figure out what our x hat and our y hat are. So let's do x hat. So that's just each point here, each of our x points, minus the mean. So it's going to be 1 minus 4, 3 minus 4, 5 minus 4, 7 minus 4. And this calculates to minus 3, minus 1, 1, 3. So that's our x hat. And our y hat, same idea. We'll just use the y values instead. So it's going to be 6 minus 3.75, 4 minus 3.75, 3 minus 3.75, and 2 minus 3.75. If we do that, we get 2.25, 0.25, negative 0.75, and negative 1.75. So there we go. We've calculated our x hat and our y hat. All we need to do now is calculate our r. So we need the dot product, x hat, y hat. And all this is going to be is take each corresponding entry in our x and y vector, multiply them together, and then take that sum. So this is going to be the first entries, so negative 3 times 2.25 plus negative 1 times 0.25 plus positive 1 times negative 0.75 plus 3 times negative 1.75. And if we calculate that, you can check exactly negative 13. Great. I'll box that just so I have it within easy reach when I do the rest of my calculation. Now I just need to figure out the norms. So let's go ahead and do it. So we have that. Let's do the norm of x hat. So that's going to be the square root of each of our entries in x hat after we sum them all, after we square them, and then sum them all, I should say. Okay, so let's go ahead and do it. So it's going to be, let me get my pen here. It's going to be minus 3 squared plus minus 1 squared plus 1 squared plus 3 squared. So you can check that that is going to be the square root of 20. And I'll just leave it like that for now. Again, that's an important number for my calculation, so I'll put a little box around it. And then finally, I need the norm of y. So let's figure out, or sorry, I should say y hat. So the norm of y hat, well, that's going to be, maybe I should scroll up a little bit so I can actually see my numbers here. There they are. So it's going to be the square root of 2.25 squared plus 0.25 squared plus negative 0.75 squared plus negative 1.75 squared. So let's calculate that, and you should get the square root of 8.75. And that is our next number. So there's the three numbers that we need. We can just calculate r quite easily now. I want to give you a little tip here to help you calculate, I think, to avoid rounding errors and kind of dealing with taking two square roots. But as a reminder, if you have a square root of a times the square root of b, well, that's just the same thing as the square root of a times b. Square roots play very well with multiplication. So I can use that just to help me out a little bit so I don't have to deal with too much rounding with my calculator. Okay, so now r is going to be our dot product, which was negative 13, or x hat dot product y hat, and then over the norm of x hat, which was square root 20, times the norm of y hat, which was the square root of 8.75. But I'm going to rewrite this just to help me out a little bit. Square root 13 over the square root of 20 times 8.75. So that'll just help me if rounding ever becomes an issue. I'm rounding fewer times. Okay, so let's put that into my calculator, and I guess roughly negative 0.9827 to 4 decimal places. So that's our R value. And a couple of things I just want to point out, that this negative here, if you get an R that's negative, this tells us that we have a negative linear relationship. So it'll always be the same sign as the slope of your line of best fit. And for the most part, the values of r have the same kind of idea of r squared. The closer you are to 1, then the stronger the relationship. So if it was exactly positive 1, then you would have a positive linear relationship that's perfect. If it was exactly negative 1, then you'd have a perfect negative linear relationship. So now that we have r, we can calculate r squared, just to make sure it matches up with what we had. So r squared is going to be r squared, which is, well, it's going to be negative 0.9827, whatever was in our calculator. In fact, I wouldn't round. I would just keep what was ever in my calculator, and then I would square it, and you can check that you get 0.966 rounded to 3 decimal places. So the exact same r squared that we calculated in the previous example. So this is just another method of calculating your coefficient of determination, and it gives you a new calculation for your correlation coefficient as well. It kind of plays the same role as the coefficient of determination. The closer you are to 1, the better the relationship. And what else do I want to say? But you do have a sign, and that sign is going to be the same sign as the slope of your line of best fit, or your linear regression line, and that tells you if the relationship is a positive relationship or a negative relationship. So this is a good way of calculating r squared as well. If you ever have any problems where you need to calculate the coefficient of determination, then this is a reasonable way of going. You can use this instead of the method you learned in the last video.